discuss that. So yeah, so I'm happy that about 10 or 12 students have submitted their answers. In fact, I don't have the time to check that, so maybe in the evening I will have a look at it. So today, we are going to discuss a different network model, that is adaptive resonance theory. It is in short called ART network. Okay. So today we will discuss that this particular interesting network. So far we have discussed various models, which includes supervised and unsupervised, right? In the supervised, we've talked about perceptrons, multi-layer perceptrons. Then in the unsupervised, we discussed self-organizing maps. Then we have seen LVQ network the other day, right? Upfield networks. Then several other networks we have seen so far. There is an interesting network, the adaptive resonance theory network. It has, as the name itself is telling, it is resonance, right? Every word, if you pick adaptive resonance, you will find that the similar functionalities in the network. That is one aspect. So if you notice, there are several interesting aspects in the network. So basically it was proposed in 1987 by Grossberg and Carpenter. These two scientists have proposed this particular network. Number one is, it is in feature wise, it is unsupervised model, and it also based upon the behavioral model. In fact, this is one of the unique aspect of this particular network. Okay, I hope all of you are with utmost attention and listening to the discussion. Then it is unsupervised, behavioral based, and it is also competitive in nature. Okay, and it, as it is competitive in nature, in the sense, obviously you will try to find a winner node, and once you find the winner node, the learning is unsupervised, and hence weight adjustment would be done. The learning would be done for the winner node. Okay, so weights updated or learning over winner node, because it is unsupervised competitive model. Now the point is, the interesting thing here is that that's what is so far with happened with the so far all other networks. Here it doesn't mean that since the node is the winner node, it can update its weights. There is a caveat there. There is a condition here. Okay, so even if the node is winner node, sometimes if winner node do not satisfies, okay, if winner node do not satisfy one particular condition, I will tell about what is that condition detail later. If the inner node do not satisfy a condition, it becomes inhibiting node. Okay, this is interesting aspect. So far what we have done was, we took it by granted, we took it as a granted, in the sense every winner node would automatically, if there is a learning, will perform the learning. And in fact, if you look at the self-organizing map, not only the winner node, but also the the topological neighbors are also exciting, in the sense that they were learning. Okay, but in this case, If the winner node do not satisfy one particular condition, then it becomes inhibitive. Okay. And another interesting aspect is that your output nodes or cluster nodes, since it is unsupervised, the cluster nodes, output nodes are flexible in the sense, when I say output nodes, it is number of output nodes or cluster nodes. That means you look at so far what are all the problems we have discussed, especially for unsupervised environment. Your number of nodes in the output layer, they are fixed, right? Hello?
Yes, sir.
The art is having a flexibility in the sense that, imagine during the learning, if you find a pattern which is not suitable to any of the clusters that are there, then you can create a new cluster. Hence, new clusters can be formed even during learning. Are you able to follow? Hello?
Yes, sir.
That means, imagine if you were given with a network having n number of nodes in the output layer, but during the learning process, you have encountered, you means the network has encountered a particular pattern which is not close to any of the cluster nodes, any of the n cluster nodes, then you have the flexibility to add n plus 1th node, the cluster node. Is it not that what we do in typical cases? Hello? Imagine you have some group of objects. I said, look, you please group these objects into 2 clusters. But while doing that particular grouping, you encountered one particular object which you found that that certainly would not belong to any one of the cluster. So obviously you will create another cluster, right? Say that I'm making 3 clusters and push this new pattern to the 3rd cluster. Is it not? Hello?
Yes, sir.
That's what is the behavioral aspect. Okay. So that flexibility, you don't find it in the previously what we have learned, because your network is fixed. We said m number of nodes in the input, n number of nodes in the output. Your topology of the network is fixed, but here it is not so. And because of all these properties, the ARC network is having a unique feature or ability to address stability, plasticity dilemma. Okay, stability and plasticity dilemma. Remember, this stability and plasticity dilemma is one of the important phenomena that is there for all the networks. Okay. What is this stability and plasticity dilemma? Okay, now let us look at what is stability first of all. All of you are able to follow what we are discussing? Hello?
Yes, sir. Yes, sir.
Yes, sir.
Okay. Let us see what is stability, plasticity dilemma. So first let us focus on what is stability. See, the stability of a network, okay, stability of a network is like this. We have seen, say, take an example, self-organizing map, or for that matter, backpropagation network for the classification. what we were doing, you are giving x1, x2, x3, x4 are the, say, 4 patterns. That means 4 objects you have. In case of classification, you may be having the target. In case of the clustering, obviously you will not have the target, so they are asked to group into some 2 clusters. In case of classes, imagine that they have to classify into 2 classes, right? So you present x1, then you perform certain weight operations, then you will identify which class or cluster this particular x1 belongs to. Accordingly, you will modify the weights, right? Hello? That's what we are doing, right?
Yes, sir.
Then after doing the modification of the weights, what you are doing? You are presenting x2, right? To the network.
Yes, sir.
And you are learning for x2. You are performing the learning activity for x2. Update the weights. Then again you give x3, perform the updating of the weights. Then you submit x4, then perform the updating of the weights, right? So this is the typical process that what happens. So far, if you notice, in typically when you are solving the problem, so this is one iteration, right? This is one iteration, right? Because you completed weight modification at the 4 objects, right? One iteration. Hello?
Yes, sir.
Yes, sir.
No, this is one iteration. See, the point is, so far what are all the problems, solved out examples or practice questions that you have done? We did it with one iteration, but we have not written any program and took a complex network or a simple, little more complex problem and made some more number of iterations. If you do that, probably you would actually, what you notice is x1 is actually belonging to the class 1. Okay, and when you move to the iteration 2, actually from class 1 it may skip to class 2. Possible, right? Hello?
Yes, sir.
Not only for classification, even during the clustering, when you do the iterations, what happening? See, x1 is belonging to class 1 and x1 actually when you submit the input, it is also belong to the class 1 as per the network. But what you are doing is when you present x2, when you present x3, when you present x4, they are not belonging to the same classes. Obviously, you are modifying the weights. When you modify the weights, there are chances that the x1, when you move to the next iteration, x1 may push to the next class, right? Possible, right? Hello?
Yes, sir. Possible.
All of you are on the same. Are you able to follow what we are discussing?
Yes.
So the stability of the network deals with this particular problem. If this type of slips from one class to the other class during the iterations, if the network is not making, but it is learning, finally the weights, it is called the stability. Okay. When you want to ensure that the stability is maintaining, there are chances that you will lose you will have the plasticity problem. So we understood what is the stability. What is the stability? When once you have a particular class or a cluster was identified correctly for a particular object, during the process of learning, when I say learning, not for, because for that particular object object learning is done, but during the process of learning of the other objects, when you keep changing the weights, if your network is pushing the correctly classified object to the incorrect class, then obviously your network is not stable, right? Hello?
Yes, sir.
That's what is this stability issue. Network is supposed to maintain the stability, means once if for x1 if you have identified the correct class, even when you are making the learning for the remaining objects, if when you move to the next iteration, the correctly classified object class should not get changed. That's what is the unique the stability feature of the network. Now you need to maintain the stability of the network. Now the point is what happens with the plasticity. When you are trying to ensure that the correctly classified objects are not slipping their classes, if you are ensuring stability, what happens is this brings plasticity problem. What is plasticity? If you notice, when you present x1, x2, x3, x4, and you have trained the network, the point is you are giving a new pattern. Okay, when you are trying to make the network to learn the new pattern, okay, when the network is trying to learn the new pattern, say take an example x5, network still should be able to perform the new pattern. So learnability, learning the new patterns while maintaining stability. Okay, during the learning process. That means what? Imagine I have learned x1. It is correctly classified. Now I am learning x4. I should be able to learn x4. At the same time, I should not spill over to another class for x1. That is the stability. I should learn x5. That is the plasticity. You understand?
Sir, can you explain the difference again?
Okay, it is like this. Okay, it is like this. We are in which module?
Third module.
Third module. You have learned first module?
Yes, sir.
Second module?
Yes, sir.
Now you are learning third module. Now you tell me you are learning the third module is disturbing your first module learned knowledge?
Sir, it is not because of the third module, but because time has passed and I haven't revised.
Yeah, see, please
No,
answer
sir,
the
no,
question.
it isn't.
No, so that means your learning in module 3 is not allowing you or not making you to forget what you have learned in the module 1, right?
Yes, sir, it's not.
Generally it should not, and since you are a VT student, it should not be further. In case if it is happening, God has to this thing, right? So it's like that. So the point is that when you are incrementally moving, you learned module 1, move to module 2, you learned. Obviously, that is supposed to augment what you have learned in module 1, and module 1 you should not forget. So the point is that the stability means, number 1, not forgetting while learning module 3, not forgetting module 1. Okay, that is what is the stability. Hope you are able to follow now.
Yes, sir, yes. That one.
What is plasticity? You keep module 1 in your mind, right? Can you say that, sir, I have already learned module 1, learned module 2, module 3, module 4, no, sir. Can you say that? Module 4, no, sir, I cannot learn. Can you say that?
No, sir, no, I can learn.
That's what is learning that is what is the plasticity. So the point is, you learned module 1. By learning module 4, you should not forget module 1. That is the stability issue. If you are forgetting, the network do not have the stability. You understand?
Yes, sir.
Now the point is, you learned module 1, you learned module 2, you learned module 3. If you say that, sir, I cannot learn module 4, that is plasticity.
Got it, sir.
Yeah, all of you got it now? Yes. Who was that asked that question? Because I'm not able to see who was asking questions. Who was that asked that question?
Sir, Akil.
Akhil. Thanks, Akhil, because this, in fact, I did not thought of this example before the class, and I was just thinking and then explaining it. Rightly, you asked the question, and I was trying to understand, trying to give you a better example so that you guys will understand the stability plasticity issue. The point is the neural networks, because remember, the point. See, the neural networks is not with the simple four objects that what we are giving two output nodes, with that simple networks, right? So typically, if you notice, there will be a large networks. So what happens is when you are trying to make the network to learn, you need to understand if the network would be stable or not. Okay, the network behaves in a stable manner or not. And another thing is, yeah, network is able to learn, but at the same time it is having the plasticity in the sense that it is able to learn the new patterns while already maintaining your stability. That means maintaining what you have learned, you are learning the new patterns during the learning process. That is what is the plasticity. Can we do that? That is the dilemma. The art network, because of its ability, it is able to address. Generally, what happens, sir? I have read this one, sir, so I forgot that, sir. What was taught in the previous semester year, sir? I forgot that because this semester no classes are going on. This Ashwini Kumar every day is taking class for 50 minutes. Though he is asked to take only for 40 minutes, he is taking for 50 minutes. We have so many assignments, so I forgot that, sir. So the point is, that is the stability plasticity dilemma. So the art network, because of its unique features, it is able to maintain the stability and as well as the plasticity. Okay. The reason is that why it is able to maintain the stability and plasticity is this. What is that? Even the cluster units that are identified as the winner, they will not be entering into the learning until and unless they satisfy a particular condition. Okay, and there is a external parameter called reset parameter that resets the network if that condition is not satisfied. So like that, there are certain unique features that are not there with other the other networks. So as we have said, it is unsupervised, and it is it is a competitive network. And so what happens when it is a competitive network? How do you identify the winner?
Sir, either we identify the lowest distance or the greatest input, net input.
Yeah, how do what the dot product, right? So it is not through the distance, rather it is through the cumulative input. That is, so it is not through the distance, but through net input. Okay, that means when you say net input, what is that? Dot product. So when you do the dot product, you identify the minimum distance or minimum dot product or a maximum dot product. Which one node will be the winner?
Maximum, sir.
Maximum.
Maximum node is the winner, right? Node with max dot product is winner. Now imagine there is a tie. Okay, imagine two nodes are with same output, or sorry, same net input. Okay, in such case, winner is okay. If tie, winner is identified based on the node index. Okay, what do you mean by node index? First node and second node. So node 1, node 2. So index of the first node is 1. The second node is node 2. So obviously the node whose index is minimum, that would be identified as the winner. So that means node 1 would be the winner when there is a tie. Got the point?
Yes, sir.
And another important thing, as I've said, you can add the you can add if you require, you can add output nodes or cluster nodes, okay, if required. And learning on winner node happens due to resonance. Okay, this is another interesting aspect. As I've said, adaptive resonance theory. I said that in the previous slide, winner node will not always give you a guarantee that the weight modification happens. That based upon the resonance. Okay, so when the resonance, when you we know that echo and all that, so you can orient towards those principles. When there is a resonance, the strength of the resonance will indicate whether weight has to be modified or not. We will see what is that strength of resonance and all. Now the point is, the ART network is typically of two types. One is called ART1, another one is ART2. Okay. ART1 network is basically deals with binary patterns. ART2 network deals with real or continuous patterns. First, let us focus on the ART1 network. Okay. So typically when you notice how the ART1 network looks is like this. You have an input layer. You have an interface layer. And you have recognition layer. Okay. This is called as F1A layer. This is called F1B layer. This is called F2 layer. So if you see here, an input layer with m number of nodes, node S1, S2, so on, Sm. These are the nodes in the input layer. Okay. So you will have same number of nodes in the interface layer. That means you can call them as X1, X2, so on, Xm. Remember, the S1 node is connected with corresponding X1 node. S2 node at the input layer is connected with corresponding X2 layer. Okay, so it gives you a one-to-one mapping between each node. Like, S1 node connects with X1 node, S2 node is connected with X2 node, Sm node connected with Xm node in the interface layer. Now in the recognition layer, you have n number of output units called Y1, Y2, so on, Yn. Okay, so these are all like output. You call them as output, you call them as cluster or whatever it is. So when you notice the connections from interface layer to the recognition layer, there are two-way connections. Okay, so you call interface layer to the recognition layer as bottom top connections. So imagine I am representing it like, I is equal to 1 to m, j is 1 to n. So you have the connections wij. Okay, so x1 node is connected with y1, y2, y3, so on, yn. Similarly, x2 node is connected with y1, y2, so on, yn, right? Similarly, I said reverse also possible. So you have connections coming back because we said resonance, right? So there should be an activation coming back. So it's called resonance. When it comes to the back propagation, we talked it as back propagation. We call back propagation also, no problem. But the point is that their error is getting propagated back. Here it is resonance. Okay, that is the difference. You need to understand. Don't think both are same. So the point is the connections from recognition layer to the interface layer are called top down. Okay. So you call that connections as WJI. Okay. And remember, in between there is a signal called reset signal. Okay, which takes the input from input layer and interface layer, then gives the signal to the output layer or recognition layer. This is the network architecture. Is the network architecture is clear?
Yes, sir.
Any doubts?
Sir.
Yeah.
So the mapping from input to interface layer is 1:1, but between interface and recognition, all of the nodes are connected with all of the
Correct. Correct.
other persons.
Correct. So x1 is connected with y1, y2, so on, yn. So that's the reason why we said wij. So that means when you say x1 to y1, it is 1, 1, x1 to y2, it is 1, 2, and so on. It's a bottom top, and it is the top down. Is that clear?
Yes, sir.
Any doubts again?
No, sir.
Okay. So there is a reset signal. What the purpose of the reset signal it is please listen very carefully. If you notice, you submit the input. There are no connection weights. If you notice, there are no connection weights between your input layer to the interface layer. Your activation just propagates to the interface layer. So the purpose of input layer is like a facilitator takes the input, pass it to the interface layer. Then interface layer sends this to the recognition layer, the activation, over the connection weights that are there from bottom to top. Obviously, you are going to have net inputs at the every node, right? Now, what we said, node with the maximum activation is the winner. Imagine you have some, say, yk somewhere here, you have some yk. Imagine that yk node is the winner. As per our so far learning methods, yk node connection weight should get changed. But the point is here, yk node connection weights do not get changed. What happens? Since yk is the winner node, the yk resonates back its activation to the interface layer through top-down connections. So the winner node propagates or resonates its activation to the interface layer. Okay. So at the interface layer, what happens? It receives the input from the recognition layer, and it also has the input coming from the input layer. It verifies a particular condition called whether these particular two things are satisfying a parameter called vigilance parameter. Okay. So what the interface layer is doing, it checks resonance values coming from winner node, and it verifies with the vigilance parameter. If the values are below that vigilance parameter, then your reset signal fires to the recognition layer so that your YK node becomes inhibition node. So that means it will not learn. Are you able to follow?
Yes, sir.
Yes.
So I repeat again, you have identified the winner node, that is the YK. What happens? Now YK resonance back, sends its resonance back. When I say it's sending its resonance back, what it is doing? It is sending its activation back to the interface layer. How it is sending? Through the top-down connections. Through the top-down connections, it sends its resonance to the interface layer nodes. Now remember, interface layer nodes are already having the inputs in the form of coming from the input layer. That particular value and the resonance value that is coming from YK would be compared against a parameter called the vigilance parameter. If the value between the input layer values and the resonance value nodes, if it is exceeding the vigilance parameter, then you will be allowed you will allow the YK node to adjust the weights. Otherwise, the reset function will fire inhibition signal such that YK will be sending the inhibition. That means it will not be allowed to adjust the learning. This is the philosophy of the ARC network. Is that clear?
Yes, sir.
So this is a very interesting network, and which if you notice the diagram that is given in the book, it is what I have narrated in the this one. When you compare, okay, now you see the so this is the diagram. Of course, you can correlate that with the diagram what I have drawn here. So now if you notice, this is your input. Input layer with M nodes. This is with your output or cluster with N nodes. Okay. Now you have the reset signal here, which is receiving input from input layer and also from your interface layer. So another thing is you are calling this as the interface layer. You see the connections. If you notice, the input layer is transmitting the input to the interface layer. That's all. The interface layer is propagating that particular inputs to your output layer, or you call that as a recognition layer or whatever it is. Okay. While it is sending, it has the connection weights. Remember, there are no weights here between input and interface. Here you can notice it is bottom up from interface to recognition, top down from recognition to the interface. And remember, when you are having the bottom up weights, of course, there is a criteria how to fix the bottom up weights. Okay, that we will be discussing it in the algorithm. But when it comes to the top down weights, they are binary in nature. So the connection weights in the top down are binary. These are all real value. Okay. How do you calculate how do you fix that? That we will see little later. So the real valued connections between bottom up, binary connections between top to bottom. Okay. Now once you send this, the activation, you identify the winner node. See, I'm just repeating what I said in the previous slide. The reason is to re-emphasize or re-illustrate. So once you identify the winner node, say take an example yj, you don't simply adjust the weights. Rather, what you are doing, you are sending that particular the activation back, resonating its the back, sending its resonance to the interface layer. Okay, or kind of an echoing the activation to the interface layer. How it is sending? Through the binary weights. Now the interface layer has received the activation from Y node. Imagine Yj is the winner node. It has received the activation. Now you have a vector, X vector, with the activation received from the Y node. Similarly, already at the interface layer, you have an S vector receiving the inputs from the input layer, right? Hello?
Yes, sir.
Now, what happens? You check the ratio of this newly received inputs from the recognition layer, already received inputs from the input layer, the ratio between these two vectors. Okay, norm of the ratio, NORM norm. So norm of X by norm of S. What is that ratio? If it is exceeding the vigilance parameter, then Yj would be allowed to perform the weight modification. If not, then Yj will become inhibition. Okay. Is that clear? Hello?
Yes, sir. Sir, what is that magnitude of like X and S, that bar?
Yeah. This is the norm of X. This is norm of S. That indicates how many number of positive units in each of the vectors. So take an example. You have the activations coming from Y2X layer that can be represented in the form of X. Now there may be a positive ones, there may be a negative ones. Similarly, when you are sending the inputs, remember we are talking about the ART1 network. Remember this is the ART1 network. What is ART1 network? That I said in the previous this one. ART1 is the binary patterns, right? So when you have the binary patterns, obviously you may be having ones and zeros here, and similarly ones and zeros here. So your norm of the vector X, norm of the vector S indicates number of positive units over X vector, number of positive units in the S vector. The ratio of that, if it is exceeding the vigilance parameter that was already given in the algorithm, then you are allowing Y node to perform activation or the learning. Otherwise, no. Is that clear?
Yes, sir.
Okay, so you can it's already 3:45. Shall we have a look at the algorithm or shall we do it in the next class?
Next class, sir.
The next
Next class, sir.
Okay, you tell me your network will be stable and plastic, or it will be stable but not plastic, or it will be plastic but not stable.
Sir, it will be both.
Both the guarantee that, right?
Yes, sir.
Okay, very good. Just out of this one. So, okay, so I'll pass here. We will see the algorithm and we will see the algorithm and a problem in the next class.